Oh, yo, wonderful people and physics lovers. You on Physics with Daniel Dallas. I open a new series related to thermal physics, thermodynamics, and I want to start from a gas state equation related to ideal gas model. I will consider some assumptions related to the gas so that we can call it ideal gas. And I'll also share my opinion about normal conditions. So that's sometimes significant for problems. So make sure you understand what they are. All right, and let's go to theoretical basis about how we can model the gas. So you understand three states of matter. The gaseous state has the simplest model. So that's definitely because the force of interaction between molecules or atoms of gas are very small. So that state of the matter is pretty easier compressible. And if you're saying about motion, what type of motion for molecules and atoms, they can freely to move. All right. So we can therefore use that everything we know about how we can describe the motion of particles and apply these concepts in order to describe the gas behavior. All right. So that's why we need to make some assumptions related to the gas in case we want to simplify our modeling. All right, so first of all, let's have a look at assumptions. Obviously, molecules should represent basically atoms. That's going to be one atom molecular in that case. And the first assumption is that the molecules represented by atoms, single atom, should be considered as perfectly elastic spheres with very negligible size. All right. Why elastic spheres? Because during collisions, they need to behave like perfectly elastic collision that you observe in kinematics and dynamics, right? So there, we need to consider them also identical so that apply our formula to the whole class of particles, all right? And of course, there shouldn't be any force of interaction between them so that each atom should have only kinetic energy and there is no energy lost due to perfectly elastic collision and there is no potential energy of interaction. So that means if one atom approaches to another one, it shouldn't have any other force except the force of interaction. But that's internal force, right? During collision, atoms colliding with another one behaves like perfectly elastic, so their momentum is conserved, right? And energy is also conserved in that case. All right, hope you understand that. And so I told you about the size as well, so that should be considered as, of course, tiny one. And the total volume of the atoms, basically of the gas, in comparison with the volume it occupies, should be considerably small. All right, so that means it's pretty, it's not dense, definitely gas. So the average concentration should be very, very small. Okay, so under this assumption, we can consider gas and problem in the context as being an ideal gas so that we can apply equation of gas state. So equation of gas state basically connects microscopic parameters like pressure, volume, and temperature. All right, so that equation looks like the product of PV, pressure by volume, is going to be proportional to the temperature when the mass of the gas or number of moles are not changing. So that means I can consider as the following. So if I put nu, sometimes, in different books, they use another symbol like Greek M. So it's going to be, I think, I'm not sure. Okay, yeah, I'm not sure about Greek letter, but so we can use nu or this symbol interchangeably. So we understand this as number of moles, okay? So that's number of moles, and times R times T. All right. So R is a constant 8.31. You can find in reference. All right. But if we rewrite, so we can write this equation in different ways, because number of moles, I will use this new and forwards, and this number of moles can be expressed through a number of molecules over constant of Avogadro. So that's around 602 times 10 to the power 23. All right. And we also can express that through the mass. So another notation that we can use, or another form of this formula for the gas state that connects all three microscopic parameters or values or quantities. It's going to be if we express number of moles through, let's say, mass over the molar mass. All right. So that's how we can express, and that means this gas state will have different presentation. So for example, in most cases, you will operate this formula. Okay. So make sure you understand how you can express, and don't forget that mass just by definition is just simply density. Let's say rho times V, what stands for volume. All right. So we can use different ways how we can describe the how we can rewrite the equation of the gas state. And you understand that this equation is applicable only for gas that fits the idea of ideal gas. All right. So as you can see here, this is the gas state. So that means if we consider some process, we need to understand that that's going to be state 0 or state 1. Let's say state 0. And during some process, in different way, the gas state might be changed. Okay, so that means gas state after being changed will go to state, just state. Okay, and this is the process that takes place. For example, during the process, some parameters might stay the same. For example, if the pressure P stays constant during the process, we will arrive to the process where volume and temperature might be changing. There is, in most cases, number of moles stays the same, except for you have deal with problems where you have leakage of gas or just transfer gas from one volume into another one. So we definitely that's clearly show you that the number of moles in a given volume is changing. All right. So hope you understand that. Okay, so it might be the process where the temperature remains the same, sort of isothermic process. Here's in this case when pressure stays the same, it's called isobaric, where the pressure is not changing. And also there might be the case when volume stays the same. So you can consider either case 1, either case 2, or case 3. I hope you understand that you can rearrange parameters. And what normally we need to do, we need to write parameters and gas state for state 0. P0 V0 equals nu 0 RT0. And for final state, PV equals nu RT. So in case if some parameter stays the same, for example, if pressure stays the same, you indicate it with putting the same index P0, indicating that the pressure is not changing. So if temperature is not changing, you, instead of putting 0, index 0 for pressure, you put index 0 for temperature. And it works pretty like the same, okay? If number of moles is not changing, in most cases, you just use the same number of moles, okay? And that's the basis. That's the basis. Now let's have a little talk about conditions, normal conditions. What does mean normal conditions? So normal conditions are conditions where you have normal atmospheric pressure, which is around 10 to the power 5. So if you wanted to indicate more precise value, so you can have a look at the reference, and there's going to be 101,325, as I remember, Pascals. So in both cases, you will use Pascals. But sometimes in many problems, you might be given atmosphere. So one atmosphere corresponds to 10 to the power 5 Pascals. Okay, that's normal atmospheric pressure. In some cases, you might be given millimeters, and you'll need to be able to convert that. So, but that's what is called normal conditions. So we use that parameter as a normal condition. All right, so that's normal condition. So also another one, temperature. What about temperature? So you know that temperature might have two types of units. So at least using Kelvins or Celsius. Of course, there might be another units of measurements for temperature, but in most problems you'll be using Kelvins and Celsius. So in that case, under normal condition, we understand that it's going to be 273 Kelvins. That's the normal temperature. 273, so normal. Or sometimes you might use in this index 0, 273 Kelvins. All right, so in Kelvins, how to convert Kelvins into degrees? Simply to the degrees you add 273. So that means when temperature in degrees is negative 273, you'll have absolute 0 in Kelvins. All right, but make sure you understand that if you want to find change in temperature, so change in temperature in Celsius is going to be the same as change in temperature in Kelvins, because two scales basically have the same step. So that means change of 1 Celsius, change in temperatures correspond to change in 1 Kelvin using another scale. So hope I clarified that. So make sure you understand this concept. So this formula is the key formula here. And don't forget that during the process, you need to keep track of the parameters changing during each process, and make sure you understand. Also, it's all about how you can visualize by plotting the graphs, but it's about simply visualize the formula for a given case. All right, I don't recommend to memorize what's happening, like what sort of formula take place when P constant or T constant, V constant. Just simply put that as the constant and express change, and you'll see how it works. All right, so it's pretty easy, and I don't recommend to memorize each type of law, right? Just better to understand, and every time just derive quickly. It works pretty fast. All right, hope you will understand that. That's sort of theoretical basis, and in the next video I'll show you how you can apply this knowledge in order to solve problems. All right, you were with Daniel Dallas. Hope you like that. Don't forget to subscribe if you're new here, and smash that like button, subscribe, and stay with us. See you next time.